Hey everyone, and welcome. Today we're going to pull back the curtain on the hidden logic that pretty much runs our entire digital world, algorithms. They're the invisible instructions behind everything from your music playlist to solving the most complex scientific puzzles. And that brings up a really interesting question. So let's just do a little thought experiment. Imagine for a second a computer that was infinitely fast. I mean, it could do any calculation instantly. No waiting, no loading bars, just boom, done. In a world like that, would we even need to care about different ways of solving problems? Would the whole idea of studying algorithms just be pointless? Well, the answer, and this might surprise you, is a huge yes. Absolutely. Because, before we even think about speed, we have to know two things. Is our solution actually correct, and will it ever finish? I mean, think about it. An infinitely fast computer that gives you the wrong answer or just runs forever in a loop. Well, that's completely useless, isn't it? And that brings us to our first big idea. We need to start thinking of algorithms themselves as a kind of technology every bit as important as the physical computer chips they run on. So, what is an algorithm really? At its heart, it's just a procedure with three really strict rules. Number one, it has to be correct no matter what you throw at it. Number two, it has to eventually stop. It can't just run forever. And number three, when it does stop, it has to spit out the right answer. No exceptions, no excuses. And this is where things get really cool. Choosing the right algorithm can be the difference between a problem being solvable or impossible. Seriously, a smart, well-designed algorithm running on your laptop could totally blow away a clunky, brute force method running on the world's fastest supercomputer. That's how much of a difference the method makes. It's that powerful. Okay, to really see this in action, let's take a look at a super simple, everyday problem and see how two different algorithms tackle it. The problem is just sorting, putting a list of numbers in order from smallest to largest. We've all done it. It seems basic, but it's one of the most fundamental things in all of computing. It's the secret sauce behind your sorted emails, ranked search results, pretty much your whole social media feed. And how you do it? Oh, it matters a lot. So we're going to compare two ways to do it. On one hand, you've got insertion sort. This is the intuitive way. It's probably how you'd sort a hand of playing cards, right? You pick up one card at a time and slide it into its correct spot. Simple. On the other hand, you have merge sort. This one's different. It uses a clever strategy called divide and conquer, where it keeps breaking the problem into smaller and smaller pieces until they're ridiculously easy to solve. And right here, this is where you see the mind-blowing power of a good algorithm. Look, for just 10 numbers, whatever. The difference is tiny, but let's scale it up to 1,000,000 numbers. That simple card sorting insertion sort, it would take 1,000,000,000,000 operations. 1,000,000,000,000. Meanwhile, merge sort, with its smart divide and conquer trick, gets it done in about 20,000,000 operations. That's the difference between a few seconds and, well, maybe a few decades. It's just a completely different universe of efficiency. So what is this magic behind merge sort? Well, it's not just a one-off trick. It's actually a really powerful general strategy that computer scientists use all the time. It's called divide and conquer. And yeah, the name pretty much says it all. Instead of trying to wrestle with a giant complex problem all at once, you just break it apart. It's a simple three-step recipe. First, you divide the big problem into smaller, bite-sized pieces. Second, you conquer those little sub-problems. And often that just means you apply the same logic to them until they're so tiny they're trivial to solve. And finally, you combine all those little solutions back together to get the answer for the original big problem. Simple, elegant, and incredibly effective. All right, let's zoom out for a second, because this whole divide and conquer idea is just one tool in a much, much bigger toolbox that's available for solving problems. The whole field of algorithms is just packed with these creative strategies. I mean, besides divide and conquer, you've got things like dynamic programming, which is all about remembering previous results so you don't have to calculate the same thing over and over. You have greedy algorithms, which always make the choice that looks best right now. There's linear programming for optimizing complex systems, and you even have randomized algorithms, which use pure chance of all things to find a solution. Each one is like a specialized key for a different kind of lock. But all this leads to a kind of humbling realization. See, not every problem has a nice, clean, efficient solution just waiting for us to find. Some problems, they live right on the edge of what we can even hope to compute. We call these NP-complete problems. The easiest way to think of them is like they're all part of this exclusive club of super, super hard problems.
For this entire group of problems, nobody in all of history has ever found a truly efficient algorithm. And here's the kicker. They're all connected. If you could find a fast solution for just one of them, you would instantly have a fast solution for all of them. A discovery like that would literally change the world overnight.
The most famous example is probably the traveling salesperson problem. It sounds so simple, right? A delivery truck has to visit a bunch of cities and get back home. What's the shortest possible route? But as you add more and more cities, the number of possible routes just explodes. It grows so fast that checking every single one becomes physically impossible, even for a supercomputer.
And this is basically a huge warning sign for programmers and scientists. If you find out that the problem you're working on is NP-complete, trying to find that perfect lightning-fast solution, well, it's probably going to be a massive waste of your time.
So what do? We don't just give up. We get clever, and we get practical. Instead of hunting for that perfect, optimal solution, we use something called approximation algorithms. These are designed to find a solution that's good enough, one that's provably close to the best answer, but in a tiny fraction of the time. Which kind of leaves us with one final thought. From making sure our programs are even correct, all the way to defining the absolute limits of what we can compute, algorithms are this fundamental, powerful technology that shapes our world. So here's my question for you. If you had a magic wand, if you could have the perfect, super fast algorithm for any one problem you can think of, what seemingly impossible thing would you choose to solve?